Hello, students of science. In this video, we're going to start talking about nuclear chemistry, but of course, we have to first start talking about the nucleus. The nucleus, of course, made up of small subatomic particles. Protons and neutrons, which are both found inside the nucleus of atoms, are collectively called nucleons. So anytime we're talking about either protons or neutrons, we can use those interchangeably with the term nucleons. Here's essentially the nucleus. We would say that is composed of nucleons. In nuclear chemistry, we call an atom a nuclide, and the number of protons and neutrons is always going to be listed. Here we're looking at a helium nuclide, 2 protons, 2 neutrons, and of course 2 electrons. But for nuclear chemistry, what's happening on the inside is the most important stuff. So here, for an example, is a helium atom and the components that make it up. Don't copy this. So of course, helium atom is going to have 2 protons, 2 neutrons, and 2 electrons. Here's the atomic mass for each one of these. Proton is that, and then so I should be getting this for my total number of protons, this for my total number of neutrons, and this for my total number of electrons. The total mass should work out to be this, if you just add up the component parts. It's like adding up the engine plus the tires plus the metal, like all the different parts of a car. This is what you should get. However, imagine you added up the individual pieces for a car, and the total amount was actually less than that. So the actual mass of a helium atom is less than we would predict. So we have this discrepancy, also called the mass defect, of 0.030377 atomic mass units. That's not a lot, but then again, it shouldn't be anything. If you added up the parts of a car, they should equal the car. It's not like when you assemble them, you get less energy. But that's what happens at the atomic level. So the question is, where did that mass go? So this part I want you to copy down. E equals mc squared, Einstein's famous equation. The missing mass of 5.044 times 10 to the negative 29th kilograms was converted into pure energy, 4.54 times 10 to the negative 12 joules. Again, we're not talking about big numbers here, but at the same time, that number you would think should be 0. So we have this missing mass was converted into energy. That is very, very important when it comes to figuring out the energies that are involved with nuclear reactions and nuclear chemistry. This is called the binding energy. That's the energy from the missing mass released when a nucleus is formed. So imagine when you took those car parts and you assembled them into a car, it released energy. That's where all that missing mass went to. The binding energy per nucleon, remember that's your protons or neutrons, is the binding energy of the nucleus divided by the number of nucleons. And you'll notice right here, if you graph this kind of out for all the different atoms that we have, where mass number increases, so this is number of proton, we did a lot of binding energy with something like hydrogen, which we saw, and kind of a lot with uranium, but you'll notice that it's this kind of smooth, with a few exceptions right here, curve down where iron is at the bottom. Iron has the least amount of energy. That higher the binding energy per nucleon, the more tightly those nucleons are going to be held together. So we can see that hydrogen is bound together very, very tightly, uranium less so, but iron, of course, is going to have the least binding energy per nucleon. This relates to things with fusion and fission. We are going to be releasing energy if we are going to be fusing things together anywhere from hydrogen to iron. Energy is going to be released through fusion, and energy is going to be released through fission anything higher than that. More on that in a little bit. All you need to know is that intermediate atomic masses have the greatest binding energies, and those are the ones that are most stable. So in this case, iron is going to be our most stable element. Fusion and fission essentially are both working their way towards iron. Stability is dependent upon the number of protons or neutrons that we have. It's kind of an interesting graph. It kind of looks like this pretty little thing here. What's important is notice this little dark line that sort of runs through the middle here. So the number of protons is going to be on the y-axis. Number of neutrons is going to be on the x-axis. What you notice is that you can't just arbitrarily throw together a bunch of protons and neutrons. They have to fit together very, very specifically. If you go outside this narrow little range, you're going to get these things that these pretty little colors means that they don't last for very long. Some of them on the order of 10 to the negative 15th seconds. That's not a lot of time. So you have this very, very narrow range of acceptable combinations of protons or neutrons. The most stable nuclei usually have both an even numbers of both protons and neutrons, and that ratio starts about 1 to 1 at the lower atomic numbers. Like if we were to do, something very low, we were looking at helium before, 2 protons, 2 neutrons. So that one has a 1 to 1 ratio. However, as you go up and up and up in atomic number, increasing the number of protons, this band sort of sweeps upward, going from about a 1-to-1 ratio with the lower stuff to about a 1.5 to 1. So here we're seeing this would be a 2-to-1 ratio, this would be a 1-to-1 ratio. It starts to sweep up toward this 1.5 to 1 ratio. So for every proton that you add, on average, you're looking at about 1.5 neutrons are going to be added there. So it starts out 1-to-1 ratio, sweeps up a little bit higher there. When you get to the higher stuff, you need more neutrons per proton to keep it stable and make sure it doesn't go all splody. Nuclear reaction is a reaction that affects the nucleus of an atom. So here we have the nucleus of an atom. An alpha particle is going to hit it, proton spits off, and oxygen comes out. So we start with one element and we are changing that into a different one. That's a nuclear reaction. No real chemistry took place. Electrons didn't switch, but the protons definitely did. A transmutation is the change in the identity of a nucleus. That's the number of protons, the atomic number. So here I have a fast-moving particle, in this case a alpha particle, hitting the nucleus of something, and we're going to get a new element spat out at the end. When we have a balanced nuclear equation, just like balancing equations before, we have to have the same number of atoms at the beginning as you do at the end. In this case here, the total mass needs to be the same. The number of protons in both the reactants and the products is going to be the same. Now this is going to be a little bit weird because they're almost looking at this as a negative proton, but really what you're looking at here is when this is going to be combining, that's going to be creating a neutron when you combine a proton with there. More on that later on, but look at this total mass. It doesn't change. 196, that's my protons plus neutrons at the beginning, is the same at the end. 28 protons and neutrons at the beginning. Even after it spits out a positron, you still have the same rough mass at the end. 226 is 222 plus 4, 73 is 0 plus 73. So those number of protons might be switching a little bit between reactants and products, but the total mass doesn't change. That's the law of conservation of mass at work. So again, here's just kind of a balanced one here. Here we have uranium-238. That's not the dangerous one, or at least not dangerous for atomic bomb explosion. Breaking down to form thorium-234 plus an alpha particle right here. But you'll notice that that total mass, so that's going to be 238, is going to be the same at the beginning as it is at the end. 234 plus 4. The number of protons is 92 here. Here I have 90. Those missing protons spat off in a helium nucleus, essentially. The total mass is not going to change, even though those protons and neutrons might start switching a little bit. The total mass will remain the same.